Hey everyone, welcome. To follow the Jupyter Notebook that I'll be going through today, you can either go to this bit.ly link right here to access the GitHub version of that Jupyter Notebook I'll be going through today, or you can go to, once you go to that GitHub link, you can similarly go to the Google Colab version of it as well. And then I'll give you a moment to try to read the bit link and then access it. Awesome. And then I'll show it later on if you didn't have time to catch it. All right, and then for this Jupyter Notebook, or you'll be going through and having some installations. So just some of the installations that you'd be required to install. If you don't have anything related to this in your environment, you could just do pip conda installs or pip installs within your Jupyter Notebook or the Anaconda prompt you'll be working with. And about me, I'm a data analyst at Autodesk. I enjoy coffee, running, and working on side projects whenever I can. You can follow me on any of these platforms, Twitter, GitHub, website. And yeah, this is A/B testing in Python. And my name is Raul Maldonado. And we'll be going through the raw formalization of A/B testing or online experimentation in Python, and how at a minimal level, how would that implementation look like in production, or say you are working on that at your job now. And for this presentation, the information and data presented today has no affiliation with Autodesk or my day-to-day work. It only just pertains to the examples and discussions that we'll be having. And the agenda will be a brief overview of intro to statistics, relevant statistics that we'll be utilizing in our discussion, an overview of A/B testing, the actual implementation, results, ending remarks, and then hopefully some questions if we have enough time. And yeah, enjoy. So imagine a scenario where you as a user are searching for, say, a truck on Google search. You enter in something, relevant keywords to your search, and the results pop up from that. And hopefully, pertaining to that, there'll be some relevancy to that. And within those search results, ads can appear as well at the top of those search results. And they would be at the top. And here, for example, I just looked for like trucks for sale, and some ads would pop up. And imagine we have a ad campaign called A that is relevant to the ending search results, and we want the user, as a business, we want the user to enter in our website. And what that would look like from our end, or a platform that's supporting tracking that information, this data would show like either a username, email, or an ID, or a universal ID, quote, UUID. And a related action to that, maybe a campaign associated to that potential click, or no click, or what's called an impression, and then a timestamp or date relevant to that. And then similarly for that ad campaign, say we had, if you notice, another campaign called B, and pertaining to campaign B, we'll talk about that a little bit more in just a brief moment. But that's the existing scenario from a user perspective. And then for us as a business, our experiment goals is for, at the core of what our objective is, we just want the user to just enter on our website, and aspirations to hopefully have them become a converted customer for whatever product or service or offering that we have had from that ad. And so at the core of this objective, we just want the user to click a button and go into our website. And then before going into the introduction of A/B testing and then continuing further from that scenario, let's just create some fake data and then just talk about some of the statistical introductory concepts that we're going to work on and utilize in our A/B testing. So here I provided an ad hoc function just to generate some data. Just run that through if you're operating on that Jupyter notebook right now, and the end results you should get is something similar to this as a data frame. You'll have two different data frames, data frame called campaign 1 or campaign A, and then campaign 2, respectively campaign B, which I previously mentioned. And results may vary. So if you run this function over and over again, you'll get a randomized set of output for your resulting data to work on within your, as you're working on alongside this with me. Okay. And a quick stats overview that I previously mentioned. We're gonna quickly talk about the concepts of or definitions of mean, variance, and standard deviation to utilize within our A/B testing process. So the mean is the calculated total sum of values divided by the total count of these values being all summed up, or in this formula right here, this mean would equal this this definition, and going down into an implementation of what the mean would be, how that would be calculated. So we have the first five values of campaign A, which are here. 9, 15, 13, 6, and 13. Take the total sum of that, we would get a total of 56. And then dividing the count of those values, we get an end result of 56 divided by 5, which is 11.2. So that's what the this definition would look like in implementation. There, and then now for the variance. Variance is the measure of spread of a given set of values for your given array, and it's defined as this formula right here. So it's the sum squared differences. No, the difference of the difference from the mean for each value squared and the total sum of them divided by the total number of values. And here's the calculation of that variance right here. So we first take the differences of those original 5 set of values subtracted by the mean that was previously calculated. Take the square root of the power to 2 of those values. Take the total sum and then divide it by n to get the resulting variance value. And then the standard deviation is similar to the variance. It's just the square root of the variance. It's seen and defined as this formula right here. So taking the square root of that previously mentioned value, it's kind of cut off. But taking the square root of that would be somewhere around like 2.5, I think. Yeah, it's kind of cut off. Okay. And then now for that, from that quick overview of intro to statistics, that will be the concepts that we'll be utilizing in A/B testing. Let's actually go through the overview of A/B testing now. So recall there's 2 ad campaigns, A and B. A was the original one from our original search for a truck sale, but then we also had a campaign B that was established that we'd also want to implement and show and expose to a different distinct set of users as well to compare, and we want to compare the performances between these 2 ad campaigns, though they would be very similar with differences of, say their call to action. For example, campaign A could be something like, can I have the text click here please? And then ad campaign B would have something very similar to that, but with the call to action, it would say learn more here. And a quick example of that is, say this is campaign A, and that truck sale that you're potentially looking for, this an ad came up for that, and you decided to click that. And then the call to action here would be click here, please. And then for campaign B, say if you had that out there, you would have a similar style of that ad campaign, but in the text or call to action, it would say learn more here. And now we want to understand the performance between each ad campaign. So should we just, by observation, once seeing the performance of these two for a given set of time and a given set of number of users, should we just either performance and just kind of guesstimate like which one is better, or is there a better method to compare these two ads? So statistically, one method we can turn to is for A/B testing for determining this online experimentation. But what is A/B testing? A/B testing is a randomized online experiment between two variants, A and B. It could also be between different variants, though there are different assumptions, calculations associated with that. And today we'll be going through just the comparison of one group and comparing that between that and another group. And this comparison is done through one comparison of a single metric of choice with assumptions as well. And essentially there are adaptations of hypothesis tests, but just reframed in a different manner for maybe marketing purposes or something to pitch to business leaders, say like, hey, we can do an A/B test, and they kind of have the context, and then also the potential benefits in the business context to implement. And just in a summary, A/B test, or like just like hypothesis test, but just reframed in a different way, a different cool way. Yeah. And then an overview of A/B testing, just in an abstract, and I found this visualization very appealing by Alan Downey on an article published in the 2000s called Probably Overthinking It. But we have a initial null hypothesis or assumption of indifference. We have data from that, and then with the comparison to these two data, we do a calculation through a test statistic, and then through some threshold or the observed effect, this delta star value, we determine and compare for this test statistic calculation and that threshold in determining if the comparison between these two groups is statistically significant or not. But that would be under the assumption of we would go in through the implementation of ensuring that there is no difference between the two groups, and I'll talk about that more in depth. But this is just like high-level abstraction of what the A/B test implementation would look like. Okay, and then within that test statistic portion, there are also a lot of assumptions needed, and also how you curate and determine the types of questions you formulate to determine the right test statistic to calculate, because in fact there are a variety of options for calculating your test statistic depending on the objective that you're trying to reach, the questions you're asking, but also the type of data that you have and like what amounts of data you have as well. So the source is just grabbed from an online PDF file from an academic website. The source is kind of hidden. If you in Jupyter Notebook, you'll see a hyperlink to that. But in those statistics courses, what they introductory statistics courses help you out in determining is like, okay, let's go to like one side of the spectrum and see for some type of data and size of data what calculation or what decisions you would need to go through to make your calculations. And then also as a next level to that is, okay, what about the other side of the spectrum of like different types of data that you'd look at, or like proportions, and how would you determine a test statistic calculation based off a branch of dependencies on what you need to make for the decision of your test statistic. And then commentary to that is there can be some comparisons between two tests, like the t-test and chi-square test. The implementation we'll be going through for this discussion will be going through proportion z t-tests and z-tests and using the functionality of that. But equivalently, what we're going to go through can be done through chi-square tests as well. And then chi-square implementation would be in the additional information section of that Jupyter notebook. And there's just a lot of spiel right now going on about like in preparation for the actual A/B test. So thank you for bearing with me. It's a lot to wrap around and also compact into the initial portion of the presentation. But let's go ahead and get started with going through and running a A/B test implementation. Keep in mind the following procedure. We're going to state our hypothesis, have a lot of assumptions and a lot of preparatory setup or mentions of that preparatory setup, do the analysis or the actual calculation of that test statistic in that overview abstraction I talked about from Alan Downey, and then make a conclusion out as well and have some like ending remarks from that that test. And then keep in mind to be careful in the construction of the A/B testing as well, and the commentary and a little bit more discussion about that would be mentioned in the conclusion and ending remarks. All right, so let's go through testing. So initially, I mentioned again that we want to have a metric of choice to utilize in our A/B test implementation. And we wanted users to at least click our call to action to enter into our website, whatever that may be, literally whatever that may be. And within that, we would want to have the success to what that event was, and there's a particular metric of choice of that, and at core is became as like a core like foundational metric for like the emergence of online A/B testing, which was click-through rates. Now there are other metrics of choice to utilize outside of click-through rate, but that would depend again on what your business objectives are or what your objectives are for your experimentation or what you're trying to evaluate. And the click-through rate is just defined as the total number of successes or clicks divided by the total number of events. And the total number of events is the summation of the successes plus those not so much successes, or what's called impressions, for an online experimentation. Okay, and so now we want to state our hypothesis. We come at the initial assumption for our click-through rate for both respective campaigns, A and B. Let's define them as P, or the click-through rate P hat subscript 1 and respectively P hat subscript 2 for campaign A and B respectively, and state the initial null hypothesis that, hey, the click-through rate for campaign A, there is no difference between that and the click-through rate for campaign B, or the D equals 0. The difference between these two is insignificant or is equal to 0, where D is defined as the difference between those two click-through rates. An alternative hypothesis is D does not equal 0, which is the difference between these two is substantially not, they actually are not like indifferent. They have some statistical difference to them. And respectively, also within our statement of our hypothesis, we establish a level of significance alpha and set that to equal 0.05. And this is just one permutation of stating your hypothesis, particularly with the alternative hypothesis. There are 3 different ways you can state that the alternative hypothesis. You can have a difference on both sides, one side or another side. Very vague, I know. I have a visualization right here to help that and explain that out. So here we have our distribution from our data, and we are right here at this point where a value d, this is just a borrowed source, does not equal to some value, which would be 0. And so we would want to see for alternative hypothesis, is there a difference in either direction? And if there is, does that calculated test statistic value fall within the range, within this probability range, which in this case right here would be alpha divided by 2 and alpha divided by 2. But in one test, one-tailed tests for A/B tests, we can have this set to equal alpha and alpha. And there's another visualization that will depict that as well, what the alpha value would look like. But these are the 3 different choices for your alternative hypothesis within your statement of your hypothesis. And again, this just depends on the question that you would want to ask. And then here again, I want to emphasize that we are under the assumption that there is no differences between the 2 ads. And we're trying to determine if there is a significant difference between the 2 ads, or what are, more abstractly, what are between the, are we trying to identify if there is a statistical significant difference between these 2 groups? And the reason why I emphasize this is because you wouldn't, it's very cautious and risky to come in front-facing and determining and try to show with conviction that there is a difference, because that, and in a similar analogy, you wouldn't want to be going into an evaluation of something and already be justified as being guilty of some action that you've been accused of, which in fact you may not be guilty of something. So that's the analogy I have there for why we should focus on coming into the A/B test implementation and coming at a standpoint of there is no significant difference between these 2 groups. And then I mentioned a level significance value alpha. What is that? I haven't quite explained that in the previous slide, but that is our level of significance, and it's the probability of a study or an online experiment rejecting the null hypothesis H naught, given that the null hypothesis were true. And then similarly, we would have a confidence level 1 minus alpha, so 1 minus 0.05, which is equal to 0.95. That is the probability of failing to reject the null hypothesis, given that is true. And that would be considered like a true positive, seeing the visual coming up. But then also there's other 2 considerations you should have between between your decision and then what is the reality of in your comparison. Beta is the probability of failing to reject the null hypothesis H naught when H naught is false. That is the probability of sticking to our ways, given that there is statistical evidence that the alternative scenario HA, or the alternative hypothesis, does exist. And lastly, the probability you mentioned is 1 minus beta, which is considered power, as the probability of rejecting the null hypothesis H naught when H naught, or the null hypothesis, is false. And then a quick commentary that the alpha value and power levels are traditionally just set to 0.80 and 0.05 in academia examples, and then a lot of online tutorials. But depending on your implementation or the background you're in or what you're trying to study for, this alpha and beta value, or your level of significance and power, could be different depending, again, on that scenario. For example, in quantum physics, this alpha value would be substantially like smaller than what is traditionally shown, especially right here in documentation. And the following now, as I promised, there's some visualization of what I summarized between alpha, 1 minus alpha, beta, and then 1 minus beta. This is borrowed from ML resources on accuracy, precision, like the beginning introductory discussions on regression in ML. But what I can bring to this analogy is that alpha value is a type 1 error. It's a false positive, where you where you reject the, this is saying is like you reject that there is no difference for like, oh yeah, there actually is a difference, but in fact, there was no difference. So that's our type 1 error. And then a true positive, which would be that 1 minus alpha or confidence level. We would have a true positive, which is our 1 minus beta value, or that power value I mentioned, and type 2 error would be beta. And another visualization to show for that is, say this is our null hypothesis and this is alternative hypothesis. Imagine this area was a little bit more, this area was increased a little bit more in this set alpha, but this is another visual representation of what's going on. This is our, again, probability of that false positive. Here is that probability of a type 2 error. And then here's our power, and then right here would be our confidence level. And then there are a lot of basic assumptions, again, that I mentioned pretty ad nauseum, but there's a reason justification for doing that, is you have to ensure that the experimentation framework is set up appropriately, because you don't want false positives to occur depending on how you calculate your metrics or how variant your data, your collected data could be, because there could be, in a business, other implementations, testing implementations occurring at the same time that you may not be aware of. There could be production issues where your data is not appropriately coming in from one or many data sources. There is how is your sampling distribution being out for a user assigned to a campaign if they're participating in that experimentation? Is it truly random, or are they, and also is their assignment random and distinct where they wouldn't go into the other ad campaign as well if they refresh their Google search? And then also the assumption of central limit theorem as well as and then that's just a discussion on sample size, which can be covered later on if there is enough time at the ending portion. And then I'm going to skip this portion, but it's basically a data transformation of our pre-existing collected data set and showing the distribution of what that data would look like for the click-through rates. And notice say for example, a size of 1600, utilizing central limit theorem, the distribution of those click-through rates would approach some normality as the size of your data would become more big. Okay, and now for analyzing the results, we'll be utilizing the proportion t-test calculation. There again there's one other type of way to calculate a proportion value, particularly click-through rates, which I'll come up to pretty soon or towards the end, which is right here is the t statistic calculation is equal to that difference d minus 0, or 0, where 0 is that initial value of there is no difference between those two groups, and divided by a standard error. And the standard error would look like this formula right here, where it's the, it's right there. And then when comparing these two groups, just note the notation that the difference is equal to the difference, or the click-through rate proportion of ad campaign 1 minus ad campaign 2. And let's go ahead and go through this manual approach. The function I utilize to create this manual approach was a bit long and went over the slide. So I went ahead and chunked it out bit by bit. So if you're following along in the Jupyter Notebook, after cell 37, you'll see markdown files of what that breakdown of the function would look like. So in the initial portion, we have our parameters for group 1 and group 2, a set alpha value, and then what our printed out alpha information would come out to. And then this is all a customized function. If you utilize it, say, in a non-data frame object, you may get some errors. So, but yeah, again, this function is just utilized for our discussion here, and is manually created. So right here we have the calculation for our click-through rate for ad campaign 1. So we're just getting for that group or data frame this total sum of those clicks divided by the total number of occurrences that have occurred, the summation of occurrences of successes and impressions or non-clicks. And then similar for ad campaign 2, we would get a similar click-through rate calculation. Taking the difference of that, we'd store it in a variable d. On to the next portion of that same function, going down, we would calculate the standard error. Since these values are more under the assumption of independence, we can calculate a p overall. The first standard error portion term within the standard error I showed previously, utilizing p overall, and then we similarly calculate the standard error term within that square root value for the overall standard error. And then going down, we manually calculate the t-statistic value that was defined in this function right here. So let's go down. Here, so d minus 0 divided by that standard error. And then we have a degrees of freedom being calculated here. So the total number of occurrences for the group or campaign A plus campaign B subtracted by just 2 values to give degree of freedom. And that's utilized in the calculation for our t critical value, or that threshold value we're going to use to compare to the calculated t statistic previously mentioned. Now, and this is utilized, this t critical value, that threshold is utilized in making our decision. However, there are 2 other ways to go about in making a decision, though they have their assumptions, advantages, and disadvantages coming up. And then this is just a printout text of our everything in summation from this function, soon to be outputted. This is all text as well. And the return, everything is returned in this portion right here of the function and will be shown soon. But previously I just mentioned that there's three ways to go about in determining the results of your information. There is a comparison for your t-statistic, determining if that's greater than the critical value t critical. In making your decision, there is an I view of like utilizing what's a confidence interval for your previous calculations. But then most importantly, and as a focus in resources research and like implementation, online experimentation, something called the p-value. And so this probability p-value is the probability of attaining an effect at least as extreme as the one you observe in the sample data, assuming, again, that the null hypothesis is true. And this is, again, one that's most highly utilized, but at the same time, a method for making decisions that can be abused as well. Because within this, if in the business context, if you utilize this in criteria for your decision making to business leaders, and that's the only thing that business leaders understand in the context of making a decision, then they fail to realize that the assumptions they still need to make, but that aren't translated to those leaders just because that lack in context and considerations as a statistician or as an experimenter, that information is lost. So on Twitter, there are some statisticians, grad students, hashtag stats Twitter, that do have concerns with the p-value, and also would like and highly like to mention that outside of just showing a p-value or a resulting decision from that p-value, that you also need to communicate the underlying assumptions as well from your test. And here's the output for utilizing that customized function right here. So here we have the click-through rates established right here for A and B respectively. The confidence interval calculated if needed. The calculated t-statistic, the t-critical value of 1.65 and then a p-value of 0.06. And then within this, the criteria is p less than alpha. If that is true, then we would make a decision to say that there is a statistical significant difference between between the two groups here. But since it's not in this case for this first iteration or implementation of our A/B test, we see that we fail to reject that null hypothesis and conclude that there is no difference between the two groups right now. And here's there's some comments on one in regards to that conclusion, but very quickly, there's a non-manual approach to go about calculating your test statistic, which in this case, we'll be utilizing stat model library and utilizing the proportion z-test function. And previously to what I mentioned, there are proprietary software that enables you to do online experimentation without the need of going through this low-level abstraction. And then similarly, there are open source packages available like PlanOut and Wasabi to help you with your online experimentation as well. But those packages and softwares have their advantages and disadvantages when utilizing them. But here we'll be utilizing the proportion z-test in the calculation from our two data frames, getting the total number of trial successes, the total number of occurrences for the clicks and no clicks, the value that we want to compare to, in this case is 0, and then what permutation that we need to make in our initial statement of a hypothesis. There was two one-sided statement of hypothesis, and then there was like a two-sided case. And then from that, inputting that information in the parameter of that function, we get the resulting t-statistic and p-value that is equivalent to the manual calculation from previous. And then that's just pretty much it for like calculation utilizing rate packages, methods, or proprietary software like that. And then similar to that, we have that end result decision. And however, there can be, if there are multiple iterations of the same test at some point, there could be false positive versus breach, and your statement conclusion, in some cases, though we fail to reject the null hypothesis and still stick with it, there could be cases where we could reject the null hypothesis, and in fact, that may not be true, and that's where we reach that type 1 error, or that level of significance. And within this, there'll always be testing, but in the sense of a caution, because the more ignorant we try to go and be confident in getting conclusive end results or what we hope for, then we forget the knowledge that we have in considerations we have of what if this scenario isn't true, or more simply, ignorance more frequently begets confidence than does knowledge.
Hi there. So I know this was all focused on a frequentist approach to A/B tests. Do you have any recommendations on where to find guides for taking a more Bayesian approach to A/B testing?
What are some resources for A/B testing in Bayesian sense? There is online packages, PyMC3, that is available for you to review. But then there's a slow emergence of online books and implementation of Bayesian A/B testing as well. I can't name the books off the top of my head. There's one book that I could name out, and it's available on Amazon. It's Bayesian Fun Way of The Fun Way of Learning Bayesian Statistics by William Kurt, and that's something I can provide pretty soon. Yeah.
Okay, if there are no other questions, and thank you very much, Raul, for sharing your information with us. Thank you.